Stats class. Here's lesson 8-1A, and welcome to second semester. We are at a very important transition point in our year. So I want to start by talking about the big picture of where we've been and where we're heading with this AP Stats curriculum. So the big picture is we started with exploring data. And remember the beginning of the year, box plots and histograms, and you're like, oh yeah, we learned all this in middle school. Oh, it seemed so easy at the time. Chapters 1 through 3 were exploring data, and that's what we started the year with. And then we moved on to experimental design, how to gather data correctly, in chapter 4, which you'll remember was the vocabulary chapter. It didn't feel like math, and that was a little bit strange, but also not too bad. And then it got harder, a lot harder, when we got to probability. Chapters 5 and 6 especially, but also I'm going to put chapter 7 in that category because sampling distributions are about probability. Chapter 7, it got super hard because it was stuff you've never seen before. Probability, some of it you'd seen before. And then now we're heading into our fourth theme of the year. So we did our first 3 themes in first semester, and the new piece that we are starting today is called inference. And that is chapters 8 through 12. And then there's also a chapter 13 that's not in your book that we'll do after the AP exam. All of that, in other words, the rest of the year we'll be working on inference. And that makes it a really important topic because we're giving it a whole semester. That's kind of crazy. You might remember from, like, I remember when my kids were in elementary school and they came home with inference type stuff on their homework. And I was so happy that they're using that word. It's like looking at a story and inferring what's going to happen next. It's about making conclusions or educated guesses based on what you have seen so far. In statistics specifically, inference means looking at a sample and making a prediction about a population. And we are going to spend a lot of time learning how to do that well. So that's where we're headed in chapter 8 and 9 and 10 and so forth. Chapter 7, we did it the other way around. So I want to remind you a little bit of chapter 7. We mostly in chapter 7 knew the parameter, which was the information about the population. And from that parameter, we could describe the sampling distribution of a specific statistic. And so specifically, we took something like the population mean, and then we looked at what if we took sample means over and over again and plotted them and saw what happened to them. What would the shapes, center spread, I'm going to call it SOCS, even though they usually are not outliers in a sampling distribution. SOCS, we described shape, center, and spread of that distribution of sample means, or we took a population proportion and looked at the sampling distribution of p hat. So this was usually of x bar or p hat. And basically in chapter 7, starting with what we know about the population, tell what's true about the samples. Now in chapter 8, we're going to reverse that. So chapter 8, we're going to go the other way. We're going to start with a statistic, which remember is information about a sample. We won't know about the population, but we're going to use what we know about sampling distributions from chapter 7 to estimate the population parameter. And we did a little bit of that in chapter 7 when we were doing, remember the German tanks, and we were trying to estimate the population maximum. But generally, that parameter is unknown, and we're usually not going to know what it is. And so we're going to talk in chapter 8 about how to take a sample and get a reasonable estimate of the parameter. And that's where we're headed. So we're switching the order of how we've done things. We're not in chapter 7, we usually knew about the population and then talked about the samples. Now we're going to know about the sample and go to the population. If you think about it, that second one is more useful in real life, because in real life we often don't know the population information. So that's basically what statisticians do, is they take samples and they use them to make conclusions about a population. So this is getting into what statistics is really all about, and that makes me excited. I really like, well, I like every chapter, but I really like this inference stuff because it's interesting that you can do that. There's math behind why you can do that. So that's what we're going to learn. So we're going to start with our statistic is also called a point estimate. A point estimate is a single value that you use to estimate the parameter. And we've called it an estimator before, like an unbiased estimator. If we're talking about the mean, sample mean is an unbiased estimator because each individual sample mean could come higher or lower. Now we're talking about, instead of all the sample means, we're talking about a single one, a single number that estimates the parameter. Because usually a statistician would not take lots and lots of samples and get the sampling distribution. Usually they would take just one, and they would use what they know about what would happen if they did more. So that's where we're headed. A single number that estimates the parameter. We want our point estimate to be unbiased, as I just mentioned. And these two, as we've talked about before, are naturally unbiased, so we're going to use them a lot, unbiased. And we also want it to have a low variability or spread. In other words, we want it to be pretty close to the real parameter. If we did lots of them, they'd be on average close to the real parameter, but we're saying we're going to hopefully get one that's close to the real parameter. The way to achieve that is by making it a random sample. We've talked about that before. And the way to achieve this low variability thing, I wish we were in class because I could ask you to tell me, and maybe you would know. Low variability, you achieve it by doing large samples. If your sample is large enough, then your spread would get smaller, and that would make your estimate closer to the real mean. But a point estimate is not the most useful thing we could do, because every point estimate is a little bit different, and they'll be a little bit off. And you never know if you happen to get one that's way far off or one that happens to be close. So what we usually do is, instead of just going with a point estimate, statisticians, there's a saying that says that statistics is never saying you're certain. You never say, this is it. I know that the mean is this. You say, it's close to this. And so what we normally do, and you saw a little bit of this in the warm-up, is we do an interval estimate. We use our point estimate, and then we add and subtract a little bit to say, well, we know that it's probably not perfect, so it's like between this and this. That interval estimate is called a confidence interval, and it is the topic of Chapter 8. We're going to do a lot of confidence intervals in Chapter 8. So, what is an interval estimate? It is a range of plausible values for the parameter based on what we know about the sampling distribution. So I find it easiest to understand this if you look at a picture. So let's draw this, put a dot exactly in the middle, as close as you can. So basically, this is our point estimate in the middle. We choose our statistic. In this, for most of the rest of the year, we'll be working with only two of them. It'll be either X bar or P hat. So we take our sample, we calculate something. That number is our point estimate. It is in the middle of our interval. Then we go out a little ways on each side. And that out a little ways gives us two boundaries that are the lower bound and the upper bound. And that distance that we go out is based on some calculations from stuff we learned in Chapter 7, which we will be spending a lot of time learning how to do those calculations. I'm going to say not yet, but I will tell you that this distance, this how far do you go out, is called the margin of error. And you were in the warm-up supposed to come up with something like that anyway, and we've already talked about it a little bit. Once you know what the mean is or what the p-hat is, you have to figure out just how far should you go to get a reasonably likely range for the parameter, plausible values. So margin of error is half the length of your interval. And it's calculated based on the concept of two standard deviations, which we've talked about before. So the interval, I'm going to write this as a formula kind of, except in words. The interval is the point estimate plus or minus, or in other words, we add and subtract this margin of error. And this margin of error comes from two standard deviations above and below the mean. Why two standard deviations? We talked about this in the warm-up also. I'm going to say usually because there are reasons why we sometimes would want to go further or less far. But most of the time we're going to go two standard deviations. And the reason why is that is the reasonably likely section in the middle of a normal curve. So why do we do two? It's because if you have a normal curve and you have your mean in the middle, you can go out one standard deviation, two standard deviations, right? And this covers 95% of the data. We've talked about that before. This middle piece is 68%. That's not so important. But the 95% is the reasonably likely values. If you're out in this outer region, here and here, there's 2.5% on each side. So 5% is the outer regions. That 5% is the rare samples. If you are in this outer region, you have a sample that's unusual and might be evidence that you've got the wrong mean in the first place. And that's why we use this two standard deviations thing. What we do with the two standard deviations is we say that we are 95% confident. That comes from this 95% down here, that the interval contains the true parameter. So let me repeat that again because it's so important. We take our point estimate. We calculate two standard deviations based on whichever formula we need, depending on X bar or P hat, and we'll get into that on Wednesday's lesson, so you don't have to worry about it today. But we calculate two standard deviations and we add that much and we subtract that much. And then we say, here's our point estimate, and it might be off from the true value a little bit. It might be off by as much as two standard deviations. So we're going to go that much above and that much below and say, okay, now I'm 95% sure that I captured the true parameter. And that 95% is actually, or the two standard deviations, 95% is correct, but the two standard deviations is actually just an estimate. I'm going to say approximately two standard deviations. If you want to get really accurate with this, you find the z-score that actually cuts off exactly 95%. So I want to remind you that to find a z-score from a percent, you do inverse norm. And if this is 95% here, I really want from here over would be the 95% plus that extra 2.5%. That is 0.975. So I'm going to say this is the 95% plus half of what's left, half the extra 5%. And I do that because I want to do the z-score that's from negative infinity up to this point right here. I want to know what that point is. That point right there, z, is called a z-star actually, which is special because it's a specific z, and it's called the critical value. And that critical value of z-star Actually, they usually use an asterisk. I used a 5-pointed star over there, but does it matter? No. So this inverse norm, if you do that on your calculator, you'll get 1.96, which is about the same as 2. This is the actual accurate version of Z star, which is the critical value that goes with 95%. Now, sometimes we might want to do something other than 95%. We will get to that later in the chapter, and we'll do something similar to this to calculate our Z star, which is our critical value. So the critical value is saying how many standard deviations do I need to go above and below my point estimate to get a margin of error that's the right size so I can be this confident. It's kind of weird. It's like we never say we're certain, but we do say exactly how confident we are. Because I did this 1.96 or 2 standard deviations, I am 95% confident. If I did 1 standard deviation, I would be 68% confident. And so depending on how confident you want to be, you can go further out or further in. And we'll do a lot more of that this chapter until you're really good at it. So that, I think, is enough for the intro. This is the intro to confidence intervals. We will get more in the next few days and more details about how to calculate this. But the most important thing that you need to know is right here. What is this interval that we're calculating? It is a range of plausible values for the parameter. So if I take my point estimate and add and subtract this amount I get from here to here, I'm pretty sure my real value is between here and here. And how sure am I? I'm 95% sure. That's the introduction to what we're going to be doing all chapter long. And that is it for these notes. More coming tomorrow.